I'm going to give you observational overview of FRBs, a quick one trying to set the stage for the rest of the meeting, and then also an update from the CHIME FRB project. So fast radio bursts, as we all know, they're few millisecond long bursts of radio waves. The first example, of course, is the now iconic Lorimer burst from 2007, where you can see the time on the x-axis and frequency on the y-axis. You see the burst sweep through the band. That's some TV station or some interference or something at a fixed radio frequency. And when you correct for the dispersion, you get the inset there, which is a burst of radio waves that is not there initially. It appears and then disappears, and that has never been, that source has not been seen again. The dispersion measure, the size of that sweep tells us that these fast radio bursts are extragalactic, because the value of the DM is much greater than anything the galaxy could provide. And so generally now we know that the total dispersion measure that you see in that sweep, in that 1 over frequency squared sweep, we believe is the sum of 3, and you could also argue 4 components, one due to the intervening Milky Way galaxy, and that's the term that doesn't, that you can never, defines FRBs in the sense of if your total is greater than that green term over there, then it has to be extragalactic. And then there's a term from the intergalactic medium, and then there's a term from the host galaxy, which could include the ISM of the host galaxy, analogous to what the Milky Way is providing, or it could be from the source, something in the immediate environment of the source. Now, this, you might think that, oh, this burst, it's an anomaly, a strange thing, but in fact, these things are really common. So and that's why I think that's one of the reasons they're so interesting. At 1.4 gigahertz for a rate, and here you should always specify the frequency and the threshold, because those are crucial in saying what the rate is. Roughly speaking, about 600 per day is thought to be the rate. So this is not something uncommon. This is something the universe loves to do. It was a surprise, and it's ubiquitous. I think that's particularly interesting. And I'll just mention there's been some evidence for galactic latitude dependence of the observed rate, but I think that's still under discussion. And I should also point you to two excellent recent reviews that will do a far better job than I will, because some very lengthy reviews. So if you want more information, see those papers. So one of the, there's all sorts of things to describe about FRBs. I'll start out with one that I think is very interesting. Some of them do repeat. So unlike that Lorimer burst, which nobody's ever seen again, some of them repeat. The first one was 121102, FRB 121102, about which the very next talk by Laura Spittler will be focused. The second, you see that, I think this is interesting because, it's like, constraining models in an instant. It rules out cataclysmic models for this kind of source. You could see here now the dispersion has been removed from them. This is a set of pulses from Arecibo, where you can see now some phenomenology that seems to be common, certainly to repeaters, but also to other apparent non-repeaters. Of course, now you can never know what's a repeater, what isn't, because it might eventually repeat. But in any case, you see some broad pulses, some multi-component pulses, and the other thing to notice is the radically different spectra. So you see some of them. Now, there's all sorts of beam effects going on. I'm going to come back to that. It'll be a bit of a theme, especially when we talk about CHIME. But you see there's a variety of burst morphology spectra. Some are band limited. So if we, a lot of people like to model FRBs as power laws in some band, but when you look at this, you say, power law, I'm not sure that's the right parameterization. And moreover, for at least certainly this repeater, and I'll talk a little bit more later about another repeater. Bursts are clearly clustered in time, so they're not a Poissonian process. And for other repeaters, and today there's 20 of these known, 20 repeaters in the literature. They most of them don't have enough bursts to be able to say with any certainty whether or not they're Poissonian. But certainly for this one and for at least one other, there's definite clustering. So, just the phenomenology and saying, oh, it's a source that can repeat and it can flip its spectrum and it can have all these different morphologies, that's all very quite interesting. But apart from that, it also does something very important, which is it enables localization. Not that some telescopes, and we'll hear about that, like ASCAP, can localize in real time, but for repeaters, this repeating, as long as you're patient, you can go to an interferometer and then go and look, and I'll talk about that shortly. But as an overview, so just about burst morphology, so just going through different aspects of the phenomenon. So most FRBs, I think it's fair to say, show single-peaked pulses. Like this one from Thornton et al., just a single peak. Some of them, and it's yet unclear what fraction, show scatter broadening, also as seen in this peak. And for those of you not familiar, this manifests as a frequency-dependent, convolved, frequency-dependent exponential that's been convolved with a Gaussian. That's how it's typically modeled. It might not exactly be that, but where the scattering time is proportional to f to roughly the -4 power. It's not necessarily exactly 4, but that's roughly that. So very strong frequency dependence. And the scattering, this comes from multipath scattering along the direction of propagation. That and the dispersion measure have imprinted on this source a history or some information about its propagation to us from the host, right through perhaps intervening galaxy halos, all the way to the IGM, and then to our galaxy. So unlike gamma ray bursts, where you don't have that stuff, you have there's a lot of information encoded in fast radio burst profiles that's quite interesting, and I think it's going to be a treasure trove for years to come, trying to sort that out. On the other hand, you also saw that, for example, in 121102, some of the bursts are multi-peaked and have complex morphologies, and it is sometimes hard to distinguish, complicated morphology from scattering, particularly if you don't have a wide bandwidth or if your source is itself band limited. This is actually something we're struggling with a little bit with chime FRBs. I'll show. How do you distinguish complex morphology from scattering? And moreover, it's when you have complex morphology, it's not so obvious in this burst. I think I show others where it'll be obvious. It suddenly makes you wonder exactly how it's best to define dispersion measures. So you think of 1 over frequency squared delay. But how do you optimize for that dispersion measure? It's a very interesting problem. You think, oh, just optimize for signal strength. Well, it's not necessarily the right way to do it. Sometimes that doesn't work, and I'll talk a little bit more about that later. FRB burst properties, spectra. So the Lorimer burst sort of was a little, is truly broadband, and that was over, if you didn't notice, 300 megahertz, a very, no sign of much fading, but others are not. That is, they have these naughty kind of spectra where you see definite variations in radio frequency. And notice the different size of the band here. This is from utmost, where the band is narrower, but nevertheless you see clear variations in the spectra. And on top of it, I showed you the some band-limited events from 121102. And you can see it even more so in this in another montage of a set of 121102 bursts. I don't want to dwell on it too much because Laura's going to talk about it, but in some of these events, you also see the spectra of of bursts, subbursts that are time ordered, going downward in frequency. And that's the sort of, I don't know who coined this. It's brilliant, whoever coined it, the sad trombone morphology. It's like wah, wah, wah. And so you see that actually fairly commonly. And I'll show you, we've seen it in other repeater bursts. And in bright sources, you can also see diffractive scintillation, which is telling you, again, about it's another imprint of the propagation of the source, which has a lot of information. Yeah, and so see Laura's talk shortly. So the repeating nature of 121102, so now I want to talk about localizations. So the repeating nature of 121102, as I said, allowed we could introduce an interferometer to the problem, and it required some patience because the bursts don't always cooperate, so you can sit there for hours and not see anything. In fact, in this case, there were many months went from the first observation till when it was actually seen to repeat. But with the VLA, Xiaomi et al. Localized 121102 by detecting a whole bunch of bursts. And if this was if 121102 was found at Arecibo, this was the Arecibo circles. The VLA could then pinpoint exactly where in the large error circles from the single dish radio telescope, because it's an interferometer, it could pinpoint it very precisely. And then you could go to an optical telescope like Gemini to see what's there. And this was the first time we could look and see, is there a galaxy there? How far away is the galaxy? What kind of galaxy? And it turned out, I think it was pretty surprising, it was a dwarf galaxy at a redshift of about 0.2. So the redshift was not actually a surprise. That was roughly what was expected. It confirmed the cosmological distance as inferred from the dispersion measure. Also coincident with the FRB as a continuum radio source. So you could see the flux from the continuum radio source over here, variable. So it's variable, but not, so the red points are when the FRB had its bursts, and you can see that the variation doesn't seem to, the variation in the continuum radio source doesn't seem to know much about those bursts, which is sort of curious. So this variation could be a propagation effect also of that source. We're not really sure at this point. And then you can, once you have that, you can go further with VLBI, the European VLBI network and the VLBA, to show that FRB is not merely in a dwarf galaxy, but off-center from the dwarf galaxy in a star formation knot, which right away suggests youth. And you think, this has got to be a young object. But I want to get into models because you're all theorists, and we're going to hear a lot about that. And then, of course, it's intriguing that some superluminous supernovae are also in star formation regions of dwarf galaxies. That's sort of intriguing. But in the last year or so, there's been 4 more localizations, very exciting, lots of wonderful work going on, and really none of them is in a dwarf galaxy, so I don't know what that means. But so for Bannister et al., you can see it's sort of a kind of a elliptical type galaxy. It's a little bit offset, so in this case, the position is known to be here. Ravi et al. The error region's a little large, but probably it's associated with this source here. This at redshift 0.66. This is at redshift 0.32. All cosmological, no question about this. Prochaska et al. Find the FRB coincident with a galaxy and with the foreground galaxy in front. So that presents a really nice opportunity to study the content of the foreground galaxy halo as well. And then I think a couple weeks ago, another FRB, one of the CHIME FRBs, was localized using VLBI to be on the outskirts of this elliptical galaxy at redshift. This one's really close, at redshift 0.03. So just a scorecard for the moment, 5 localizations. I put it in red. This one's a repeater. The rest are not known to be repeaters. They might turn out to be repeaters, but they're not for the moment. Sort of interesting that the 2 repeaters are in young type environments, and the others that are thus far non-repeaters are kind of, older type, maybe elliptical, maybe they're not all exactly elliptical galaxies, but older type environments. But it's really small number statistics, and I wouldn't draw too much. And then very late last night, I was sort of curious about this because I hadn't seen this plot. You can just rudimentary Python plotting skills. But this is the XSDM and redshift versus XSDM, because one interesting question is XSDM, that when I say XS, I mean subtracting off the Milky Way component, is that correlated with redshift? Because that would say that your dispersion measure is really dominated by the IGM and not by the host. It doesn't have to be that way. It could be the host contributes a lot. In fact, for 121102, the host contributes about a third of the dispersion measure. And then I took off the NE2000 galaxy. I took off 50 for the halo. I took off 100 for the host, which of course is totally ad hoc. I can't justify that, but just for fun. And then chi by I, that's DM 870 is 875 times the redshift. That's sort of interesting, but of course it's early days, and one needs more localizations, and maybe there'll be a talk by ASCAP. Who knows what they'll show? I don't know anything. I was kidding around. I don't. Yes, I'm looking forward to. Yeah. Okay. Scattering. Very quick. How much? Okay. Scattering. As I said, some FRB shows clear scattering tails. Yeah, so this is a plot now of dispersion measure, and here the excess is not removed, so this is the total dispersion measure, and you could argue it should be the excess, but it's the same for all FRBs here. And this is scattering time, and you always have to say, if you say scattering time, you have to say, at what frequency, because scattering is very frequency dependent. As you said, this is referred to 1 gigahertz. So the black dots are galactic radio pulsars, where you see a clear correlation. Lots of scatter about that correlation. This is log-log plots over many orders, but nevertheless, there's a clear correlation. The 1.4 gigahertz points are from the FRB cat, where the triangles are upper limits, and the red points are the first 13 CHIME FRB events. I'm going to add to this plot shortly, but you can see that it's not so obvious at the moment what's going on there. It may be a hint of a little bit of a correlation, which you might expect if going through if the DM is IGM dominated, you go through a lot of halos. And halos cause scattering, or you might expect it if the local environment contributes a lot of dispersion measure and a lot of scattering. There's lots of ways you might expect it, but it's not really obvious in this plot. And just to point out, and I want to start pointing out biases, because that is a big part of the FRB game that we all have to understand. You might say, how come all the CHIME events are less scattered than the 1.4 gigahertz events? The scattering times are so much lower. And of course, the reason is because CHIME can only measure those values. If you consider a 10 millisecond burst at 1 gigahertz, at 1.4 gigahertz, the width there is 2.6 milliseconds, which is very measurable. But in the CHIME band, it's 77 milliseconds, which we would have a very hard time detecting. We could, if it was bright, we'd find it, but there's a huge bias against finding. So events like these over here, we're not going to see with CHIME, or we'll have a harder time. So there's a huge amount of bias in this plot that's very important to understand. Polarization, and I think Manisha is going to be talking all about polarization, and I'm running out of time, so I might just skip it, except to give you the Reader's Digest version for those of you who remember that publication. It's just a real short summary. It's a mixed bag. Of the 109 reported FRBs in the catalog, 11 have reported rotation measures, 11, and not the same ones, which puzzles me, but anyway, 11 have reported percent linear polarizations, and I've given you the ranges. They range from 0 to 200, with one exception, as I'll say in a second, and then from 0 to 100 in terms of polarization. Some are not at all polarized, some are 100% polarized, some show circular polarization, many show no polarization. Many of the rotation measures are consistent with the Milky Way values, some are a little higher, but one is definitely not. I guess Laura's going to talk about it. I'm running out of time, but That's about 10 to the 5 for the repeating FRB 121102. Shocking value, among the highest rotation measures ever measured for an astronomical source. And once corrected, you can see all sorts of very fine features at 30 microseconds. If it's generic, then some of the if such a high rotation measure were generic, then some of the unpolarized FRBs might merely be depolarized, like perhaps the channel bandwidth was too large to detect such a high rotation measure. But I think we're coming to the conclusion it's not at all generic, even to the repeaters. The CHIME FRB collaboration has now measured rotation measures for 3 other repeaters, and in no case is it anywhere near as high. You can see the value here. This is work by grad student Ryan McKinven. So 121102 seems so far to be unusual. I'm going to skip that. Okay, so I was supposed to spend half my time on a review and half my time on CHIME, so I'm running out of time. So CHIME is a radio telescope in Penticton, British Columbia, made of 4 stationary cylinders that are 20 meters by 100 meters. So an area of 5 hockey arenas in Canadian units. It's a transit telescope that is oriented north-south, so the sky rotates overhead, and on each of these cylindrical axes is 256 dual linear polarization antennas that are all combined and put into a massive correlator that is sitting in these large shipping containers that are over here, and the FRB searching is done in that shipping container. We operate from 400 to 800 megahertz, and just to set the scale, you can see the CHIME team standing on one of the axes over there. CHIME was built and designed to do a cosmology experiment. The signals all come down to huts that are underneath the dishes that have a part of the correlator that does the time to frequency transform, and then another part of the correlator that's in the shipping container. And then the same data go to 3 different experiments, one of which is the FRB, and the other is actually mapping neutral hydrogen and high redshift. In the correlator, we form out of all of those antennas 1,024 digital beams on the sky. So the width here, depending on frequency, is about 2 degrees, but we go north-south 120 degrees. The beams have interesting shapes, interesting responses, which are highly declination dependent. I'm saying that, I'm emphasizing this for a purpose, so you understand what we're dealing with here. But we have a very wide field of view, so we can detect them fairly efficiently. You can see, so all of this, whoopsie, sorry. Yeah, I'm going to skip the whole detection thing because I'm truly running out of time and I want to show you the science stuff. This is a CHIME view of the sky. This is how we look at it. This is time on the x-axis. This is north-south beam on the y-axis. These are pulsars. So pulsars in time traverse through the primary beam at fixed declination. So north-south beam is equivalent to declination. So these are pulsars. This is a very bright pulsar, 0329 plus 54. It was sort of cool at first. So, wow, we could see it for 4 hours. And then you realize that's actually not so cool. So we showed FRBs go down to 400 megahertz. That was the first result where you, first 13 events from last year, and you can see some of them go right down to the bottom, 400 megahertz. All sorts of interesting morphologies and interesting question. Gee, if it cuts off there, are there events below 400? We can't answer that. CHIME also found the second repeater, and you can see some of the interesting morphology with the sad trombone, again, just like in 121102, very reminiscent of it. In fact, we did detect 121102. You can now, I'm showing you this partly, it's interesting that we've only seen one burst from it so far, but this is a nice plot made by Alex Josephi, who's here, he's our localization guru. And you can see how things traverse the sky through the beams. We know 121102's position, so we know exactly where in the beam it goes off, and the event happened over there. And you see there's a certain beam response that is specific to this location that you have to understand when you're interpreting these spectra. So this is just different ways of dedispersing the same burst. The top That's actually from the CHIME pulsar instrument. But these, what I want to show you here is these huge spectral variations. This is not bandpass calibrated, and what you see is we have enormous spectral changes in sensitivity across the bandpass. So this is entirely bandpass related. We try and calibrate it out, but keep in mind every single one of those 1,024 beams has a different spectral response that has to be calibrated. It's a transit telescope. We cannot just put a source there to calibrate it. It is very challenging. We then found 8 more repeaters. 8 more repeaters, variety of morphologies, interesting structure, interesting spectral response, but again, always folded in with the CHIME response, which we are working on. Complex morphologies, it makes morphological characterization very challenging. How best to de-disperse? I've already emphasized that this is something that we struggle with, and I guess a lot of you do too. Then we found some more repeaters. One of the interesting things about the repeaters is how if you plot the burst widths of the repeaters, this is pulse width now, and there's a histogram, and then you plot at least the 12 non-repeating sources that we published, you can see that there's evidence that the repeaters have wider bursts. Why that is, I don't know, but this is an observational overview, I'm telling you this. A return to the scattering versus DM plot. Again, this is total DM. I've now plotted the CHIME FRB repeaters on top of this. Again, the plot is heavily biased. We also would have, if you just only pay attention to CHIME, we'd have a very hard time finding higher, we have a bias against finding highly scattered pulses. Nevertheless, I don't know, is it interesting that these are a little higher at high DM than these? Not so clear. There's burst morphology is very much intertwined with all of this, and we're trying to sort that out. Very recently, we reported that one of our repeaters, one of the most prolific of the repeaters, shows periodic activity. So this is, we've taken all the bursts. I think in this case there were 28 bursts, 27 bursts. This is a periodogram where you can see clear periodicity at 16.3 days and harmonics. We have checked to verify that the source exposure does not contribute to this. This is if you take random events that suffered the same exposure as this source. And also a pulsar nearby on the sky. Radio pulsar does not show any of these, and there's other pulsars that also, nothing else shows this periodicity, only the source. And this plot is a very nice one, where you can see in black all of the exposure that we had to it. Very nice plot by Pragya, I don't know where Pragya is, there's Pragya. A beautiful plot, because it just shows you, we have tons of exposure here, but we only ever see the burster every 16 days. Now, some cycles, we do have some exposure. That's not a good example. Here's a good example. We have excellent exposure, but no bursts. So it's not there at every cycle, but it only appears within this 4-day window. So plot here by a bunch of students, including Ziggy Plunis, who's somewhere in the audience. There's Ziggy right in the middle. You can see that it doesn't seem to be any fluence correlation with phase in this 16-day cycle. The dispersion measure, if you look at the red points, those are the most important ones. They're from baseband data where we can measure it really well, very constant as far as we can tell. And so what is it? We'll probably discuss it. I'm running out of time, so there's all sorts of things it could be, but we don't know, and I hope you'll tell us. So I wanted to tell you a little bit more. I have 44 seconds. Okay. We're trying to catalog a lot of bursters at the moment. This is what we are doing. If we weren't distracted by that periodicity, we would have been doing a huge amount. But basically, the localization of our burst is non-trivial. The fluence is measuring fluences is non-trivial. Morphologies are non-trivial. I want you to note this plot that was published in a repeater paper made by Alex Josephi. Note the complexity here. It is really hard, getting these localizations right is not easy. And if we want to publish hundreds of these. Each one we have to be sure, we don't want to give people wrong coordinates, and we don't want to give people wrong fluences. Essential to publishing is getting this stuff right, and we are working on it. And I want to show you very quickly one CHIME FRB out of hundreds, and 3 different views. In one beam, broadband. In one beam, narrowband. It's the same event seen in these 3 different, and in one beam, it just sneaks in a little bit there. So if this event had happened like over here, we would only see this view of it. That's sobering. There's a lot of information encoded here. We have to know each beam of 1,024 beams very precisely. This is non-trivial work, and we are working hard trying to get this done for the community to tell you. But let me give you a few things that I can show you with certainty. RA deck plot, they're all over the sky. The red ones are repeaters. I lost track of where I am, I'm sorry. Okay, so I will just say our exposure is complex. Praga is working on that. We have an upper transit and a lower transit. And I'll show you one plot that you probably haven't seen yet is DM dispersion, interesting dispersion, DM dispersion, and but it is totally uncorrected, this plot, for CHIME FRB detection biases. So you see that it falls off with dispersion measure, but we don't know if this fall off is due to our sensitivity falling off or not. So you shouldn't read too much into this. We do have sensitivity out here, absolutely. So it's definitely falling off, but I don't know how fast. And we are currently determining our biases. We've set up a real-time injection pipeline where we are injecting these things and into the real data stream. Okay, conclusions. FRBs are interesting. I don't think I have to tell you that. But the story is developing rapidly. Like, I learned so much just preparing this paper last night, reading all your papers. There's unbelievable work going on in the community. There's so much more to do. And I will stop there. I'm looking forward to the rest of the workshop. Thank you.